So we'll be doing that in a couple of weeks. But today we're going to talk about section 4.4, which is curve sketching. And curve sketching, I think, is one of the quintessential skills in calculus because it brings together so many of the things that we've done up to this point. There are things in pre-calculus which come in. There are things about derivatives, things about limits. It all comes in to a head when you're doing curve sketching. And maybe that's why students are so afraid of curve sketching, because it uses so many different things. But I think if you could, a final exam could be, here's a function, graph it. And if you do that function perfectly, you probably can do anything else in calculus. Okay. So we have one objective, and that's to learn how to graph functions completely using finding their zeros, finding their asymptotes, finding the critical points, finding the local and global maxes and mins, and finding the inflection points. And we're helped by all of our machinery that we have about increasing and decreasing and concave up and concave down and all that good stuff. Now, why would we care about graphing functions? Well, for the same reason that we care about dissecting organisms, right? It's really informative to get an up-close and personal look at how these functions actually behave. And by taking apart their graphs, we can do all that. It's kind of like diagramming sentences. Do students still learn how to diagram sentences in 7th grade? Raise your hand if this is familiar to you. Okay, about half of you. So when you're diagramming a sentence, you put the subject over here and the verb over here, and the prepositional phrases, they come on down, and then you've got adjectives and adverbs all over the place. And when you see the diagram for a sentence, you get an idea of how complicated the sentence actually is. Okay? So you can know a lot about a function when you know its anatomy, so to speak. So there's this poem by C.S. Eliot called The Love Song of J. Alfred Prufrock, and it begins, "Let us go then, you and I, when the evening is stretched out across the sky, like a patient etherized upon a table." And that's what we're going to do. We're going to etherize our functions and lay them out on the table. Okay, so there's one, the increasing and decreasing test is one of the tools that we have in this regard. And it says that when a function's derivative is positive on an interval, that function is definitely increasing on that interval. If the derivative is negative, then the function is decreasing on that interval. So to take a look at the function x cubed plus x squared, here's the derivative, 3x squared plus 2x. And you can see that where the derivative is positive, the derivative is here in red, the function is increasing. Now the function could still be negative, but it's increasing when the derivative is positive. Here the derivative is negative, and you see on this interval right here the function decreases. Then the derivative changes to positive, and the function changes to positive as well. This is your punishment for letting your phone ring in class. You have to look at me dance. Okay. Like Ally McBeal, right? The dancing baby. Oh, another dated reference. Okay. Now we also have the concavity test, which tells us that you can figure out the concavity of a function by looking at its second derivative. So if the second derivative is positive, then the graph of the function is concave upward. If the second derivative is negative, the graph of the function is concave downward. So here we have x cubed plus x squared. Same function as before. Here's the first derivative again. And the second derivative is the derivative of the derivative. And it looks like this. Here's this line in orange. Where the second derivative is negative, which is here on over, we have a concave down graph. And where the second derivative is positive, we have a concave up graph. Okay, so if you have a function and you don't know what its graph looks like, you can look at its derivative to find the intervals of monotonicity, increasing and decreasing. You can look at the second derivative to find the intervals of concavity, and all that information can be reassembled to get a good picture of the graph of the function. So here's my checklist for graphing. I'm using the same points that are in the book, except I added one, and since the one that I'm adding is at the beginning, I have to call it step 0. So find out when the function is positive or negative or 0 or not defined. Sometimes you can do this very easily. You can always find its y-intercept by plugging in x equals 0. You can many times find its x-intercepts, the places where it crosses the x-axis, by solving for the equation f of x equals 0. And then you can look at where it's positive, negative, find out where the denominators or whatever of them go to 0. And so you can get a lot about the function already before you dive in and do any calculus. That's kind of like the low-hanging fruit. Then you want to look at the derivative. And it's not required to form a sign chart, but I think it's a good way to assemble or to decompose all the information about the monotonicity that comes from the derivative. You can find out when the function's increasing, when it's decreasing, and in between increasing and decreasing, you will have a maximum. In between decreasing and increasing, you have a minimum. Next step, take the second derivative and do the same thing for that. Form its sign chart. Where the second derivative is positive, you know the graph is concave up. Where the second derivative is negative, you know the graph is concave down. And then inflection points are where it switches its concavity. Okay, step 3 is to put this all together into one big chart to combine the monotonicity information, increasing and decreasing, with the concavity information, concave up, concave down. And then once you do that, it's simple as just drawing a picture which has all of those properties connected to it. Okay, so that's the simple 4-step, well, 5 steps if you count from 0, procedure. So let's look at some simple examples, and then after we do the simple ones, we'll do the complicated examples. In some semesters, I spend 2 days on graphics, so I actually have 2 days worth of examples in this slideshow. Now, I'm not going to go through each of them twice as fast so that I get all of them in one day. I will do as many of these as we can fit, and then I will post the slides for the entire set of examples online. So you get the benefit of like a 2-hour lecture because you can go and check out those slides on the website. Also, in recitation this week, I gave a worksheet with a bunch of different graphing problems. So if graphing is something which makes you nervous, then it would be good to go to recitation so you can work on that with your TA. Okay. So first example is going to be this function, 2x cubed minus 3x squared minus 12x. Okay. So what was step 0? Do whatever you can without doing the calculus. Find the zeros of the function. Solve the equation 2x cubed minus 3x squared minus 12x. You can factor out an x, right? So you know that f of 0 is 0. And then the other piece that's quadratic, you can either try to factor it, or you can use the quadratic form, or quadratic equation. And if you look at the answers we got using the quadratic equation, you might feel lucky that you didn't spend a whole lot of time trying to factor it because it doesn't have any nice rational roots to it. But there are 2 real roots, 3 plus the square root of 105 over 4 and 3 minus the square root of 105 over 4. You know, is it always necessary to solve this equation? I think it's not always necessary. It's nice that if they are rational numbers to be able to plot them exactly, but since they're not, I'm not sure. But anyway, we did get one significant point. It goes through the origin. Okay. Next step is to find the monotonicity. And we need the derivative for that, so let's take the derivative. The function is 2x cubed minus 3x squared minus 12x. Its derivative then is 6x squared minus 6x minus 12. And that does factor nicely. It factors as 6 times x plus 1 times x minus 2. So the critical points are where this derivative is equal to 0 or not defined. Derivative is a nice polynomial, so not defined is not going to happen. Where is the derivative equal to 0? X is which? -1 and +2. So we'll make a sign chart that has a line for x minus 2 and a line for x plus 1. And we know that there are critical points at -1 and at -2. We want to know what happens in between those. Okay. So for x minus 2, we know that it's negative, negative. It's 0 right here, even though I didn't indicate it, and then positive. Then for x plus 1, it's negative, 0, positive, and positive. Okay. Then the product of the two factors is going to have the same sign as the product of these two signs. So the derivative here is going to be negative times negative, positive, negative times positive, negative, positive times positive, which is positive. And so because the derivative has those signs, we know that the function is increasing between from negative infinity up to -1. It's decreasing between -1 and 2, and then it's increasing from 2 to infinity. Okay, which is great. Now we know exactly what's happening at -1, 2. What kind of point is this? This is a local max. Okay, I'll just put max there. And then 2 is a local min. Okay, yeah. In the first line, I'm taking these x's and then I'm evaluating just x minus 2. Okay, that's what this means over here. This is the sign chart for x minus 2. Sign chart for x minus 1. Sign chart for the derivative, which is the product of these two. And then that tells me stuff about the function. Does that make sense? Okay. So yeah, you can plug in a sample point, or you can just think, it's x minus 2. So it's negative when x is less than 2, and positive when x is greater than 2. Okay. Other questions about the monotonicity sign chart? Okay, great. Well, then let's pick it up a notch, and we'll look at the concavity. Concavity, we need the second derivative. I'll remind you that the first derivative is 6x squared minus 6x minus 12. So the second derivative is the derivative of that, 12x minus 6, which again factors as 6 times 2x minus 1. Now, 6 is a factor in the derivative, but the sign of 6 is not going to change as x changes. So the sign of f double prime is the same as the sign of 2x minus 1. So I really just need to look at 2x minus 1. I know that it's 0 when x is a half, and it's negative when x is less than a half, and it's positive when x is greater than a half. Okay? And I did two signs here, minus, minus, and plus, plus, because it's the second derivative, and because I can do my little trick with the frowns and the smiles. I know that it's concave down when x is less than 1/2, and the graph is concave up when x is greater than 1/2. Okay, and that tells me that this point here is an inflection point because it switches from concave down to concave up. Make sense? Okay, simpler equation because it's a linear equation and not a quadratic like in the first derivative. Okay. So then I'm going to take the monotonicity sign chart that I made, and I can really just take the last line of that. That's the most useful one. And the concavity sign chart, and I can put them together to get something more descriptive of the graph. So monotonicity, I just copied this one from 2 slides ago here. We know that it's increasing and then decreasing and then increasing some more. Concavity, I also copied over from 1 slide ago, and then I'm going to put them together. So these are the points that I know are important. -1 is a local max, 1/2 is an inflection point, and 2 is the local min. And because I'm going to graph values of the function, it helps to put the values at these points up on top of that number line there. So this says that -1 is a local max, 7 is a local maximum value. The point 1/2 comma -6.5 is an inflection point of the graph. And 2 is a local minimum, -20 is a local minimum value. Okay, and see this f of x here says that I'm plugging in these x's into the function f. Okay, now what is going on in between -infinity and -1? Well, we know that the graph is increasing, and we know that it's concave down. What shape will the curve have if the graph is increasing and concave down? Well, I like to put this all together on a unit circle. So we label the quadrants in the plane 1, 2, 3, 4, and you can think of each quarter of the circle as being a curve, and only 1/4 on the circle here is both increasing and concave down. Which one is that? How many say that it's quadrant 1? How many say that it's quadrant 2? Okay, quite a few people vote for 2. How many say that it's 3? How many say 4? Okay, yeah, the correct answer is 2. On quadrant 1, if you go from left to right, function is decreasing and concave down. Quadrant 2, it's increasing and concave down. Quadrant 3, we're decreasing but concave up, right? Holds water. And in quadrant 4, increasing and concave up. Okay? So as you're trying to, any combination of increasing or decreasing, concave up or concave down, gives you a different shape to the curve on that interval. All right? So what we know now is that the graph of the function resembles this quadrant of the circle on the interval -infinity to 1. -infinity to -1. Okay? So I'm going to put a little second quadrant arc right on that little interval there to remind me that that's the shape of the graph. Okay. Now, between -1 and 1/2, function is decreasing and concave down. Right, so let's all air graph something that's decreasing and concave down. It'll go like this, right? Decreasing, but concave down. And so we'll get that. In between 1/2 and 2, still decreasing, but now concave up. So it'll look like that. Decreasing, but concave up. And finally, between 2 and infinity, or after 2, function is increasing and concave up. So which quadrant are we talking about now? The fourth quadrant. There we go. Okay. So this bottom sign chart here has almost everything I need to graph the function because it's got the significant points on the graph, -1, 7, 1/2, -6.5, 2, -20. What kind of points those are, max, inflection, and min, and also the shape of the graph between all those significant points. So we can put that all together, and basically now we just have to connect the dots. We've got the 3 zeros of the function that I found in step 0, 3 plus or minus the square root of 105 over 4. The 2 critical points, the local max and the local min, at -1, 7 and 2, -20. And the inflection point at 1/2, 6.5. And now I just have to connect those dots using arcs that are shaped like the ones that I have already figured out. So you guys ready? Here we go. Okay, from -infinity to -1, we have something which is increasing and concave down, and we know it goes through that 0 there. Between -1 and 1/2, it's decreasing and concave down. We know it passes through the origin. 1/2 is an inflection point. Between 1/2 and 2, we're decreasing and concave up. And then from 2 on, we're increasing and concave up, passing through the other 0 of the function, or the third 0. Okay? And there you have it. We're all done. We took apart everything we could using the first and second derivative of the function. Okay? Any questions about that? Do you like my diagram? Do you like it? Sam, I am. Okay. Well, then, if there's no questions about cubics, it shouldn't be too hard to do quartics, right? So let's go ahead and try a quartic. X to the 4th minus 4x cubed plus 10. Okay. Well, step 0 would be find out where the x-intercepts and the y-intercepts are. The x-intercept is always easy. You can just plug in 0. And so 0, 10 is a point on the graph of this function. Finding the x-intercepts where f of x equals 0 involves solving a quartic equation. Some quartic equations look like quadratic equations where the variable is x squared, like x to the 4th plus something times x squared plus constant. But this is not that kind of thing. So we're not going to be able to solve explicitly the places where f of x equals 0. But there are some other things we can figure out. As x goes to infinity, f of x goes to infinity. As x goes to minus infinity, f of x goes to plus infinity, because we're taking it to the 4th power, right? Any number to an even power is going to be non-negative. Okay. Not much else we can figure out just looking at the graph, or without doing any calculus here. Okay, but at least we know one point, and we know the asymptotic behavior. Okay, next step then is to find the monotonicity of the function. For that, we need the derivative. Function is x to the 4th minus 4x cubed plus 10. The derivative is 4x cubed minus 12x squared, which is factorable as 4x squared times x minus 3. Okay. So let's make a sign chart. I'll make one for 4x squared. Now, if x is negative, 4x squared is positive. If x is 0, 4x squared is 0. And if x is positive, 4x squared is positive. So that's my sign chart for the one factor, 4x squared. Okay, for the next factor, x minus 3, I know that it's 0 when x is equal to 3. It's negative when x is less than 3. And it's positive when x is greater than 3. Okay, and the product of these two Well, the product of the two factors will have the sign, which is the product of the signs. So positive times negative is negative. Positive times negative is still negative. And positive times positive is positive. Okay, so what will the monotonicity of the function look like? Well, here the derivative is negative, so it will be decreasing. Here the derivative is still negative, so it's still decreasing, and then it switches to increasing. Okay, so what kind of critical point is this point here? A local which? It's a local min, right? Because it decreases and then increases. What kind of critical point is this one here? Yeah, this is neither a local max nor a local min. It decreases, stops, and then decreases some more. Okay? There's in a lot of the examples that you look at, there will be situations where you make the sign chart, and then you find all the critical points, and the monotonicity switches back and forth. It goes increasing, decreasing, increasing, decreasing, increasing, decreasing, all the way down. But it doesn't have to be that way. In this case, we go decreasing, decreasing, increasing. And devious calculus instructors often cook up exam problems where that happens. It doesn't just alternate. You can repeat monotonicities. Okay. So any questions about this? Good. Well, then let's look at the second derivative. First derivative is 4x cubed minus 12x squared. The second derivative is the derivative of that, 12x squared minus 24x, which factors as 12 times x minus 2. So I'm going to make a sign chart, one for 12x. And that's negative when x is negative, positive when x is positive, 0 when x is 0. Make another sign chart for x minus 2. That will be negative when x is less than 2, 0 when x is equal to 2, and positive when x is greater than 2. The second derivative is going to be the product of these two things. So when x is less than 0, negative times negative is positive. Positive times negative is negative. Positive times positive is positive. Okay. And what does this tell us about the graph of the function? I know that it's concave up when x is less than 0. I know that it's concave down when x is in between 0 and 2. And I know that it's concave up when x is greater than 2. Okay, so we have the complete monotonicity sign chart. We have the complete concavity sign chart. Now, some people tell me that they would not like to factor things and find the signs of the factors and then multiply those signs. They would much rather use this technique, which is to pick some point less than 0, plug it in, and see what sign that has. You'll get something positive, and you know that the second derivative is always going to be positive on that interval. Then pick some point in between 0 and 2, plug it in, observe what sign it has, and that'll be the whole sign on that whole interval. Then pick something greater than 2, plug it in, and whatever sign that has, that'll be the sign on the whole interval 2 to infinity. Now, you can do whatever you want. However, make your life simpler. You know, if you want to pick a point in between 0 and 2, I would suggest 1. You want to pick a point less than 0, maybe negative 1. Pick a point greater than 2, you got to be 3. But then, basically, you're interchanging algebra for arithmetic. You know, I prefer algebra. It's easier for me to think just in terms of signs. Okay, so we have an inflection point here and another inflection point here. At 0, 0, and at 0 and 2. Okay. Questions about the second derivative? All right, what's next? We need to combine the monotonicity sign chart and the concavity sign chart into one major sign chart. So the first line has the derivative and therefore monotonicity. I'm sorry that they're overlapping here. The second line has the second derivative and the concavity. Okay. And then the last line has the function values. F of 0 is 10, f of 2 is negative 6, and f of 3 is negative 17. And now I'm going to take note of the shape in between these significant points. So when x is less than 0, function is decreasing and concave up. So which quadrant does that resemble? Decreasing and concave up. Fingers, please. Decreasing and concave up. That's quadrant 3, right? Like this. Okay. Decreasing and concave down. Which quadrant? Decreasing and concave down. That's quadrant 1, yeah? Decreasing concave down. Then decreasing concave up, which is the same as this one over here. And then finally increasing in concave up. That's which quadrant? Quadrant 4. There we go. Okay. So now we have the shape of the graph between all of our significant points. And we can use that to sketch the graph. Okay? So there we go. This is the same sign chart from the previous slide at the bottom. And I've labeled all the points that I know so far, 0, 10, 2, -6, and 3, -17. Okay. On the interval 0 to infinity, or negative infinity to 0, I should say, I know that the function comes down from negative infinity, decreases concave up, and hits the point 0, 10. So it's going to look like this. Then it switches its concavity to pass through the point 2, -6. So 0, 10 is an inflection point. 2, -6 is another inflection point. And it's decreasing the whole time. It's decreasing, decreasing, all the way up to 3, -17. After that point, it increases again. So you get a curve which looks like this. Most polynomial functions will just wiggle up and down. Cubic function will go down, come up, go down again. Quartic function will go down, come up, go down, and come up again. But in some quartics, you can get those critical points to sort of collide with each other, and that's when you get something that goes down some more, and then goes up. And that's what we had here. Okay? Questions about that one? Okay. Well, now you know the procedure. Why don't we take a look at some of the other examples here, like this function here, f of x equals x plus the absolute value of x. No, x plus the square root of the absolute value of x. Okay. So everything was hunky-dory when we were doing algebra or polynomial functions, but when we start throwing in things like absolute value, students start to get a little bit worried. Well, don't get too worried about the absolute value. I know that we tend to panic, but really all that means is it's a piecewise defined function. So we just look at the pieces, look at what this graph or what this function is going to do when x is positive, what that function is going to do when x is negative, and so you'll have different equations. That just means you take derivatives of different expressions. Okay. So looking at it by itself, automatically f of 0 is 0. So we found one point. That was easy. And you can also tell that if x is positive, f of x is going to be positive, because you're adding x, which is positive, to the square root of something, which is positive. And so the sum of those two things is going to be positive. Okay, so if you're trying to find places where the function is equal to 0, we found one, x equals 0, then y equals 0, but there aren't going to be any zeros when x is greater than 0. Maybe there's a place where x is negative, that f of x would be 0. Could we solve that equation? Are there negative numbers which are zeros for the function? That would mean, is there a number x for which x plus the absolute value of x square rooted is equal to 0? Now wait a minute, you say. You can't take the square root of a negative number. I'm not. X is negative, so minus x is positive. All right? Think about x being minus 3, then minus x will be positive 3, and so I can legitimately take the square root of that. The equation I have then is x plus the square root of minus x equals 0. And that reduces to, let's see, square root of minus x equals minus x. Square both sides. If I take the square root of minus x and square it, I get minus x. Wait a minute, I thought if you squared anything, you got something non-negative. Exactly. X is negative, so minus x is positive. Then you solve that for x. This is finally a polynomial equation. What you get is x equals 0. Oh, we already got that one. And x equals minus 1. And now that we've solved it, it does make sense. Minus 1 plus the square root of the absolute value of minus 1 is minus 1 plus 1, which is 0. Okay, so these are the only x's for which f of x equals 0. We have negative 1 comma 0 and 0 comma 0. Okay, a little bit hinkier algebra there, but it's really just a piecewise thing. Okay, so what else can we tell using limits? Well, we can see that the absolute value sorry, that the limit as x goes to infinity of f of x is infinity. Because x goes to infinity, and absolute value of x will go to infinity, so the square root of the absolute value of x will go to infinity, and so the sum of the two things will go to infinity. What is the limit as x goes to minus infinity of f of x? Well, then this is not so clear. Because as x goes to minus infinity, x, that first term in the sum, is going to minus infinity. But the square root of the absolute value of x, that's going to positive infinity as x goes to minus infinity. So what would the sum be? This is an indeterminate form of the form negative infinity plus infinity. And if you wanted to write it another way, instead of saying let x go to minus infinity and find the limit of x plus the square root of minus x, you can say let y go to positive infinity and find the limit of the opposite of y plus the square root of y. Okay? Same thing. We're more comfortable with letting our variables go to positive infinity than negative infinity, so I'm just going to rewrite it. And how would I do a limit like this? First of all, looking at it, do you have a guess as to what the answer is going to be? What is your guess? 6? 6 is not a good guess. Infinity might be a guess. How many think that it's infinity? Okay. 0 would be another guess. How many think that it's 0? After all, one thing goes to infinity, the other thing goes to minus infinity. Negative infinity would be another guess. Okay, we've got the most hands for negative infinity. The reason for that being that this is a first degree function and this is a 1/2 degree function. The larger function's degree is going to make it grow faster. Okay, and if you wanted to do it mathematically sound, then you can do a little multiply and divide by the same thing trick. That will transform this to y minus y squared over the square root of y plus y. Okay, so this is now quadratic, degree 2. This is linear. Well, it's not linear, but its degree is 1. Higher degrees on the numerator, so this minus y squared is going to flood out everything else. The limit is minus infinity. You can do L'Hopital's rule on that too if you want. But upshot being the limit, I thought that was thunder or something. The limit as x goes to minus infinity of f of x is minus infinity. That'll be useful later. Okay. Now, we're finally ready to take some derivatives. The function is x plus the square root of the absolute value of x. And we can't take the derivative of the absolute value of x without taking care as to what x actually is. So let's break it up and assume first that x is positive, because then we can rewrite the function as x plus the square root of x. X is positive, so the absolute value of x is just x. And that we can differentiate the regular way. It's 1 plus 1/2 x to the minus 1/2, which we can write as 1 over 2 square root of x. Okay. All right. So just by looking at it, we can tell that this derivative is always going to be positive when x is positive, because square root of x is always going to be positive. 1 over 2 times the square root of x will be positive, and so we're adding a positive thing to 1. The derivative is always positive. So there won't be any critical points when x is positive. Derivative is always positive. Okay? And if you want to look at the asymptotic behavior of the derivative, as x goes to 0 from the right, this denominator goes to 0, but remains positive. So the limit as x goes to 0 from the right of the derivative is infinity. And that tells me that 0 is a critical point of the function. There is no derivative there. So it's one of those critical points where the derivative is undefined. Okay? And if you want to let x go to infinity, then you see that this term here goes to 0, because the square root of x will go to infinity, and it's in the denominator. So the limit as x goes to infinity of f prime of x is 1. And what that tells you is that the further out you go, the more the tangent line approaches just a straight line with slope 1. Okay, so that much we got from the derivative when x is positive. When x is negative, we have to find the derivative of x plus the square root of minus x. And that's very similar to the derivative of x plus the square root of positive x, except that we have a negative sign coming out from the chain rule. So the derivative now is 1 minus 1/2 times minus x to the minus 1/2. And if you look at the limit of this as x goes to 0 from the left-hand side, we have, again, a 0 in the denominator. Okay, but this denominator is positive, so 1/2, or 1/2 times the square root of minus x, that goes to positive infinity, but then we're subtracting it from 1, so the limit as x goes to 0 from the left of f prime of x is negative infinity. All right, we already knew that this was going to be a critical point. Now we're finding the left-handed derivative on the other side. Okay, now are there any places where the derivative is equal to 0? If we go to as x goes to minus infinity, again we get asymptotic to 1. Now when is this equal to 0? When is 1 minus 1/2 times the square root of minus x equals 0? Well, if you solve for x, then you get that the square root of negative x is 1/2. X is negative, so negative x is positive. Square both sides, negative x equals 1/4, or x equals minus 1/4. Double check. If x is minus 1/4, then the square root of minus x is the square root of 1/4, which would be 1/2, and 2 times 1/2 would be 1, so that fraction that I'm subtracting from 1 is 1, and I get 0. So here's a critical point where the derivative is equal to 0. Still with me? Okay, so it took a couple of tries, a couple of steps, but now we know the derivative completely, and now we can make a sign chart for the derivative. The function's defined piecewise. That's what absolute value does. So its derivative is also defined piecewise. And we can't really factor the derivative, but we can label the critical points. Negative 1/4, and then 0 is another critical point. And then I can, because I can't factor, the only thing I can really do is put test points in between the critical points. So let me take a test point in this interval here when x is less than negative 1/4. What's your favorite number between negative infinity and negative 1/4? Negative 1. That's a very good choice because it's easy to evaluate functions on negative 1. When x is negative 1, I'll have 1 minus 1/2 times 1, 1 minus 1/2. That would be f prime of negative 1 is positive 1/2. And so I know that the function's got a positive derivative on that whole interval. Okay. What's your favorite point in between negative 1/4 and 0? No one's ever asked you that before, right? Just pick any number between negative 1/4 and 0. But you must choose wisely. What'd you say? Negative 1/16. Okay. Now, why didn't you pick negative 1/8? Okay, because the whole point is to take the square root of something, so you might as well make your life easy and find something that has a nice square root. The square root of 1/8, who knows what that is, but the square root of 1/16, that's a 4th. And so if I plug in x equals minus 1/16, I have 1/2 times a 4th. That would be 1/2 times, 1/1/2, which would be minus 2. 1 minus 2 is negative, and so the derivative is negative on that whole interval, negative 1/4 to 0. Okay? So if you're going the method of picking sample points, which we have to here because we can't factor, make sure you make your life easy by choosing things that you can easily plug in. If you try negative 1/8, then you're going to have something that you need a calculator for, and then you won't have a calculator on the exam, so how are you going to do that? So we need to be smart about how we choose them. Something in between 0 and infinity, I suggest 1. When x is 1, f prime would be 1 plus 1/2, which is 3/2, which is positive. And so the derivative is always positive when x is positive. Actually, we'd figured that out already, right? Okay, so we now have the sign chart for the derivative. That tells us the monotonicity. It's increasing here, decreasing here, and increasing there. Okay. So what's the next step? Second derivative. But it won't be as bad as the first derivative. Okay. Yes, local max there, and a local min at the point 0, 0. Okay. All right, the second derivative is the derivative of the derivative. So let's write the first derivative in the fractional exponent form. It's a little bit easier that way. it was 1/2. It was 1 plus 1/2 x to the minus 1/2. So its derivative, pull down the minus 1/2, multiply by the 1/2, we get minus 1/4 x, and then subtract another one from the negative 1/2 exponent, we have negative 3/2 exponent. Okay? And as long as x is positive, then the square root will be positive, and the reciprocal of the square root will be positive, and the cube of the reciprocal of the square root of x will be positive, and that's what x to the minus 3/2 is. All right, so if x is positive, x to the minus 3/2 is positive, which means that f double prime, which has a negative in front, is negative. Okay, so that much we figured out. Now, if x is negative, we have a different formula for f prime, so we'll have a different thing to differentiate to get f double prime. It's f single prime was f single prime was 1 minus 1/2 minus x to the minus 1/2. We take its derivative, and again we get minus 1/4 minus x to the minus 3/2. Okay. So we have this minus sign that's here, and then we multiply it by minus 1/2, but then another minus sign comes out from the chain rule. So the three minuses multiplied together to get minus 1/4 minus x to the minus 3/2. And again, if x is negative, minus x is positive. The negative 3/2 power of a positive number is another positive number, but then we're taking minus 1/4 times it, so this is negative also whenever x is negative. Okay? So another way to write that, if you want it, is that f double prime is negative 1/4 times the absolute value of x to the minus 3/2 power. Okay, so the sign chart's very simple. If x is negative, f double prime is negative. If x is positive, f double prime is negative. And as x goes to 0, from either side, f double prime goes to minus infinity. So we're concave down for x negative and concave down for x positive as well. Okay? This is not an inflection point because we don't switch concavity. It's concave down on both sides. Okay, so we got monotonicity, we got concavity, put them together, what are you going to get? All right, now I labeled the point negative 1, 0. That's just a place where the graph crosses the x-axis, but it doesn't really change its behavior. It doesn't switch concavity or monotonicity there. Significant point, but not in terms of the change of the function. Negative 1/4, 1/4, that's a local max. 0, 0 is a local min, and then there aren't any other significant points when x is positive. Okay, when x is less than negative 1, or less than negative 1/4 even, the function is increasing in concave down, increasing in concave down. Okay, so it looks like that part of the circle. Between negative 1/4 and 0, function is decreasing in concave down, so it looks like quadrant number 1. Greater than 0, function is increasing and concave down, so it resembles the second quadrant, having a limit of positive infinity as x goes to infinity. Okay. So this should be enough, right? We should be able to put together the whole graph of the function. And I've got it all labeled here. I know that the limit as x goes to minus infinity is minus infinity, so it's going to start down here off the screen, and then it's going to go up to, oh, first I got to label my points, thank you. It's going to go up to, through negative 1, 0, up to negative 1/4, 1/4, down to 0, 0, and concave down the whole way. Okay, beyond 0, 0, it switches to increasing, but it's still concave down. So ordinarily, we've seen functions that go decreasing concave down, and then they switch to concave up before they increase. In this case, we are staying concave down the whole time. So the rest of the graph will look like this. Okay, so there's a point of non-differentiability at 0, and the graph shows a cusp at that point. Okay. So pretty cool, right? Now we've got this graph. Okay. More of the same, right? Another one to try. Actually, I think I'll let you try this one. Okay. So here's our function. F of x is x e to the minus x squared. Now you know the procedure, right? Pick off the easy points. Find out where it's 0, where it might not be defined. Limits as x goes to plus or minus infinity. Whatever you can do quickly. Then look at the sign chart for its derivative. That'll tell you when it's increasing and decreasing. Look at the sign chart for its second derivative. That'll tell you when it's concave up and concave down. And then you just have to put it all together, right? Okay, well, why don't you do that? Talk amongst yourselves.
So let's go ahead and do 30. Before we take derivatives, we can look at the limit of this function. Limit of x goes to infinity of f of x is 0. F of 0 is 0. And also limit of x goes to minus infinity of f of x is 0. Pretty clear to see that f of 0 is 0. Why is it true that the limit of x goes to positive infinity of f of x is 0? Well, x times e to the minus x squared, you think about that as x divided by e to the minus x squared. And polynomial functions
Mike, sorry, is negative when x is less than the negative square root of 3 halves, and positive later. So the sign alternates negative, positive, negative, positive. And we have 2 inflection points. Actually, no, we have 3 inflection points. Here, here, and there. Okay. So I'm sorry about the radicals in this example. You can, when you're cooking up examples, you can either have yeah, I just turned it back on. I'm sorry. You can either have, everything nice in integers, but if you do that, then they end up being very large integers. So if you want medium-sized numbers, you sometimes have to deal with radicals. Okay. So we put that all together. Oh my goodness. We've got the monotonicity sign chart on top, the concavity sign chart on the bottom, and then we plug these into the function values. And yes, because we're plotting function values, we do now need to put them into the e to the minus x squared stuff. But anyway, we know that we know the limit as x goes to minus infinity is 0. We know that it's decreasing and concave down. Okay, that it's decreasing and concave up after that. Where did it go? There. Then it's increasing and concave up. Now that's decreasing and concave down. Then it's decreasing and concave down. Finally, increasing and concave down. And we know that the limit as x goes to infinity is 0. Okay. So this bottom row here, this is all we need to assemble the graph together. Are you ready? Here it is. Okay. These are the points here. Negative square root of 3 halves, negative 3 halves e to the, negative square root of 3 over 2 e to the 3. Here's the other one, and then these points are all on the graph function. We know that it's decreasing and concave down to the first point, decreasing and concave up to the second one, then increasing and concave up, increasing and concave down, decreasing and concave down, decreasing and concave up. Okay. So there you have it all. It is kind of messy with the e's and the square roots and everything. But to find the regions of concavity and monotonicity, you only have to look at polynomials, which is kind of nice. Okay. All right. So questions about this one? Let's do one final example. I think I have 2 more beyond this one on the slides, which you can look at later on. This is just going to be 1 over x plus 1 over x squared. Okay. So find where the function is 0 or infinity or not defined. Well, when x is 0, obviously I can't take 1 over x or 1 over x squared. So that's a candidate for an asymptote. When x goes to infinity, what does f of x go to? That goes to 0. When x goes to minus infinity, what does f of x go to? Also goes to 0, because this thing goes to 0 and this thing goes to 0. Okay, so we know we have a horizontal asymptote at the x-axis. We probably have a vertical asymptote. Yeah, as x goes to infinity, as x goes to 0 from the right, we have a positive infinity. So there's a vertical asymptote when on the y-axis as well. Okay. Now, if you want to get a common denominator, you can do that and write it as x over x squared plus 1 over x squared, or x plus 1 over x squared. And that's easy to see that you have a vertical asymptote when x is 0. Okay, when is it equal to 0? Well, writing it in this form, x plus 1 over x squared, lets you know that when x is minus 1, f of x is 0. 1 over minus 1 plus 1 over minus 1 squared is, in fact, 0. Okay? You can even make a sign chart for the function like this. If x is less than negative 1, one factor is negative, the other one's positive, so the product will be negative. Whoops. Yeah, these signs are down here. You can't really see them. When x is greater than negative 1, the numerator is positive. The denominator is always positive when it's not 0. And so you get a positive function. Okay? We don't always look at the sign of the function in step 0, but you could. All right. We already pointed out where the horizontal asymptotes are as x goes to positive infinity or minus infinity, f of x goes to 0. Okay. Now the derivative, f of x was 1 over x plus 1 over x squared. So its derivative is negative 1 over x squared minus 2 over x cubed. And I got that by pretending those were power functions, x to the minus 1 plus x to the minus 2. Okay. Writing that derivative over a common denominator, it becomes negative x plus 2 over x cubed. So we have two sign charts, one for each factor, negative x plus 2 in the numerator, and x cubed in the denominator. Negative x plus 2 changes its sign when x equals minus 2. It's positive when x is less than minus 2, and it's negative when x is greater than 2. Now, when x cubed is negative when x is negative and positive when x is positive. So the product is going to be negative when x is less than negative 2, positive, is this right? This doesn't seem right. Oh, yes, negative times negative is positive when x is in between negative 2 and 0, and negative when x is greater than 0. We know that it goes to infinity as x goes to 0. Okay, so the function decreases, increases, and decreases some more. We have a local min here when x is minus 2. And this is not in the domain of the function. There's a vertical asymptote there when x is 0. Okay, step 2 is concavity. Again, looking at the derivatives this way, take the derivative of that, you get 2 over x cubed plus 6 over x to the 4th. Think about it as power functions. Put that over a common denominator, and it's 2 times x plus 3 over x to the 4th. That will be, the numerator is negative when x is less than negative 3, positive when x is greater than negative 3. The denominator is always positive except when it's 0. And so the quotient is going to be 0 when x is minus 3, negative when x is less than minus 3, positive when x is in between negative 3 and 0, and still positive when x is greater than 0. So negative 3 is an inflection point, and we can fill in the concavity in between the inflection point and the vertical asymptote, and on either side. Concave down, concave up, concave up. Vertical asymptote there still. Okay, putting these all together, we know that there's a horizontal asymptote at negative infinity. Between negative infinity and negative 3, it's concave down and decreasing. Inflection point at negative 3. Decreasing and concave down between negative 3, concave up between negative 3 and 2. Local min at negative 2. Increasing and concave up between negative 2 and negative 1. Crosses the x-axis at negative 1. Still increasing and concave up until it reaches the vertical asymptote at 0. All right? So we got, at every interval, we've got one different thing going on. And then after 0, it is decreasing and concave up, approaching another horizontal asymptote of 0. Okay? Well, very good. Now we can put it all together, and this is the graph of the function. It should come down here, go through that local min, and then go up. Okay. Well, that was kind of anticlimactic. Look at that. Okay. So that's the checklist. There are 2 more examples. Remember the checklist, and just follow it through. Graphing is like dissection, not like vivisection. Okay. Have a good weekend. I'll see you in 5 days minus 75 minutes.